So this presentation is going to be on safe learning of regions of attraction for uncertainty at certain nonlinear systems with Gaussian processes. So we're back to kernel methods. It's going to be presented by Felix Bernkamp from ETH Zurich.
All right, thanks for the introduction. So my name is Felix Bernkamp. I'm a PhD student at the Learning and Adaptive Systems Group at ETH Zurich. And this is joint work with Riccardo Morricone, who's now a PhD student at Imperial College, and my two supervisors, Angela Schellig at the University of Toronto and Andreas Krause at ETH. So in general, when we do control, we typically start with a model of the system. So in this case, a quadrotor, we have some set of sensors and some actuators. In order to control the system, we typically start by doing a modeling step and designing an abstract model of the system, which is basically a mapping from inputs to some states as they develop. Using this model now, we use our control theory toolbox, minimizing some error that we want to do. And based on this, we can design the control law, or this control policy pi, which is basically the inverse mapping, taking the state or measurements and tells us which input we should apply to the quadrotor, again, in order to properly minimize some objective error. We can then go ahead and implement this, this control policy on the real system, closing the loop from measurements to actuators, and then hopefully our system will behave in such a way as we designed it in the control theory. Now the one assumption that we make in this kind of open loop control design is that actually our model is a perfect approximation of the real world. And in practice this is not the case. So think for example of a quadrotor that when it flies very close to the ground, you may have sort of nonlinear ground effects, or if you have a robot driving around in the real world, it can encounter different surface materials, and you can typically not specify in advance all the different conditions that you may encounter. And the problem is now, if your model is not an exact representation of the real world, then in the best case you have degraded control performance, but in the worst case you can actually encounter instability. That is, your control policy actually renders your closed-loop system unstable. Now the reason for this is that there's somehow this disconnect between the real world and what we do in the control theory, where somehow there is, even as we apply this control policy in the real world, we do not use data that we generate in order to optimize the policy. Now, the solution to this is to introduce some learning, or less fashionably, online system identification, where actually see how the system behaves in the real world. We can use data in order to improve our model, and based on this improved model, we can then compute better controllers, so that as we iterate this process of gathering data, optimizing our model, and generating better control policies, we actually achieve high performance in the long term, as our model becomes an exact representation of the real world. So why is this not used in practice, right? So if this allows us perfect performance in the long run, why do people not use this? And my personal opinion is that the reason is that safety really matters in practical applications. So because what we've done here is we've created a kind of feedback loop in our design process for the controllers. And this is now a kind of feedback that control people actually don't really understand. Because as we update our model, there are now questions of, will the controllers that I generate with my updated models actually continue to be stable? And even if I have these stable controllers, how do I even excite and actuate my system so that I can actually learn about the dynamics in a reasonable and data-efficient manner? And this is sort of what we focus on in this talk, so of trying to work towards a solution for this kind of feedback setting where you actually use data to generate new controllers. And so the general question that we ask is, can we actually learn about the system dynamics while guaranteeing at the same time that we don't encounter instability during the learning process? And for this, we start by assuming a continuous time model where we have some a priori model which comes from our typical modeling step, which is the kind of typical model that you always use in control. But additionally, we assume that there's some error term, so some model that we do not know in advance, so that may, for example, represent the different ground conditions that you saw as the robot drove around in the real world. So for now, we will not consider optimizing the policy, but actually focus on a fixed control law that we implement. And we ask the question, where can we actually use this policy safely on the real system? And somehow, in order to answer this question, we're allowed to experiment, but we're not allowed to encounter instability. And the core idea is basically that we start by certifying some small region around an equilibrium point as being safe. So that's somehow saying that our initial policy stabilizes our system locally, but in a very small subspace of the state. And then in this sort of safe region of the space, we can excite our system and learn about the dynamics of our model that we want to operate. And as we gather more data about the real system, we can then update our estimate of the safe set and expand it. And as we iterate this process of learning about dynamics within the current sort of safe region of the controller, we can eventually sort of reach the maximum safe set in which our controllers actually could use. So this is in general impossible without further assumptions. So we make some very generic assumptions in our work, and specifically for the prior model, we assume that it's Lipschitz continuous. So this is an easy way to ensure existence and uniqueness of the solutions of your nonlinear ODE here. And for the unknown model, we assume that it has bounded norm in some reproducing kernel Hilbert space. And the details of what this means are not important for the remainder of the talk. They're all in the paper. But basically, it's the functions that have bounded norm in an RKHS are somewhat well-behaved functions, and that we can actually use tractable statistical models to estimate these functions. So the two main challenges that we encounter when we sort of try to tackle this problem is that on the one hand, we have to give stability certificates for general nonlinear uncertain systems, and on the other hand, we have to consider how to excite these systems. And for the stability certificates, if we have linear controllers, there's actually some previous work where you can combine Bayesian regression with robust control in order to give these kind of stability certificates for linear controllers. But for nonlinear systems, it's less well understood. In fact, so the closest work uses these reachability concepts, which for their theorems require basically solving a very complicated partial differential equation using a discretization. And on the side of the exploration, for linear systems, this is well understood. I mean, we've been doing system identification for linear systems for about as long as controllers have been around. And similarly, for finite domains, reinforcement learning with the MVPs have really considered this a lot. But again, for nonlinear systems in continuous state spaces, this is not well understood at all. So in this paper, we try to provide a solution to both of them, at least partially. And on the stability certificate side, we give Lyapunov stability guarantees for general nonlinear uncertain systems, but we only can give them with high probability over the belief of our model. And on the excitation side, we will use ideas from sensor placement, specifically exploiting some modularity, in order to actually analyze our framework and give theoretical convergence guarantees. So let's start by focusing on the stability certificates. So what we want for our controller is that if we have some state space X here, and we have some initial safe state, so this is again sort of a very small region about the equilibrium point that we want to stabilize, then we want to estimate some of the largest safe sets so that for any initial condition within the safe set, if we let our control system run, we eventually converge to our initial safe set. And in mathematical terms, it's basically written up here. And this is in general then called the region of attraction for a control policy. So how can we compute this? Well, let's start by considering actually a deterministic control system. So again, we consider a one-dimensional state space X here for illustration purposes, and then we have this one-dimensional subspace that is actually safe to use and to which we want to converge. Now, in order to guarantee this condition that we actually converge to this, one typical approach is to use Lyapunov functions. So based on these Lyapunov functions, we can now consider sub-level sets of this Lyapunov function where we basically pick some constant C and consider as an estimate for our safe set any sort of state that has a function value less than C on this Lyapunov function. And now the idea behind Lyapunov theory is that if you can guarantee that you're always going downhill along this Lyapunov function within your safe set, then you eventually guarantee to converge to a zero. Or in mathematical terms, if you can show that the derivative of the Lyapunov function along the trajectories of your system are negative, so you're always going downhill, then you actually have this implication that you eventually converge. And now if you want to find the maximum safe set, this is now just a question of maximizing this constant C such that this condition is fulfilled. So these are very classical results, basically going back to the early work in the 60s from Lyapunov. And the problem is that it's not something that an algorithm can actually check online. So the problem here is that in order to check this condition here at the bottom, you actually usually algebraically show that the system fulfills these properties. And that's not something that an algorithm can do online. To solve this problem, we consider a discretization of our state space, where tau is basically the discretization constant, so the maximum distance that a discrete point, that a continuous point can have to the closest point in the discrete domain. And now we start by checking this condition of going downhill along the Lyapunov function at only a finite set of points, namely at our discretization. In practice, of course, this is not enough to guarantee stability, but what we can do is we can exploit the continuity properties of both of our dynamic system and the Lyapunov function in order to actually check a more harsher condition on stability. So we require that at the discrete points, we're actually going downhill along the Lyapunov function by minus L times tau, but then we can sort of exploit the continuity of this entire system to actually give guarantees for an entire continuous domain. And this is now nice because this is an algorithm that actually an algorithm can check online. So there's a finite number of points for which we need to satisfy this condition, and this maximization over C, we can simply do some binary search over this parameter C. So, and I just want to point out that there's been some very related work on this, sort of independently by Bourgaty and Lazare here at CDC this year, and they focus sort of more on this sort of similar ideas for deterministic systems. What we consider here now is what happens if you now have this unknown part in the dynamics. Can we still give similar guarantees? To start out, let's actually look at how do we model these systems. Basically, given the assumption of bounded RKHS norm that we've made, we can use Gaussian processes as a tractable statistical model in order to learn about these system dynamics. And what this means is that we basically have some mean belief over the dynamics, which corresponds to our prior model. And then additionally, the Gaussian process model provides us high probability confidence intervals. So this is the region within the true dynamics will lie with high probability. And moreover, we have this property that the dynamics are actually still Lipschitz continuous, so we don't have to worry about, so we can still use the same ideas as before. So now basically this nice thing about this model is that as we get more data points, we can update our belief over the dynamics, and these confidence intervals actually shrink over time. So that in the limit, as we get lots and lots of data points, we get a very good estimate of what the true dynamics actually behave like. So how can we use this model to certify stability? Well, the first thing when we add these unknown dynamics is that we now want to certify that we're going downhill on the Lyapunov function for actually our unknown model. And now since we have these high probability confidence intervals, we can actually look at the worst case model within this confidence interval and give high probability guarantees that we're actually going downhill in this discrete number of points, and by checking the Saussure conditions, we give high probability guarantees that the system actually remains stable. So this is now nice because basically any safe set that we estimate, we're guaranteed to converge back to our initial safe set at 0. So let's see how this actually works in practice. So here we see these unknown nonlinear dynamics that we want to learn about. We pick a Lyapunov function and some initial safe set as 0 to which we want to converge. Now if we knew the system perfectly, then we could compute the derivative of the Lyapunov function along the dynamics. So this is this v dot of x here, and compare it against this minus L tau safety threshold that we've defined. Now the problem is that we do not know the dynamics actually perfectly. So we only have a belief over the dynamics, which means in turn we have a belief over whether we're going downhill on the Lyapunov function or not. Now the idea is that as we gather data now within this initial safe set, we can actually update our belief over the dynamics and in turn update the belief over v dot. Where now sort of the boundary on the safe set occurs when the upper bound on v dot of x crosses the safety threshold. Now as we gather more and more data, eventually the safe set expands as we learn more about the data, and in the limits of, after, in this case, 15 data points, we actually converge very close to where the true boundaries of the safe set are, which is this point here, where the true dynamics actually cross the safety threshold. So this now allows us to actually give stability certificates during online learning without ever leaving somehow a safe region that we actually want to stay within. So let's now see how can we actually excite the system in order to actually give guarantees, and specifically look at how can we actuate the system so that we can actually give convergence guarantees to this maximum safe level set. And the main observation that allows us to do this is that the policy pi of x that we're considering in the setting is actually safe to use within our estimated safe set. That is, if this is my current estimate of the safe set and I actuate my system, no matter which exploration policy I use, as long as on the boundary of the safe set I apply my policy pi of x, I will always remain within this safe set. As a consequence of this, we can use any exploration algorithm that now applies this policy pi of x on the boundary. Now, in light of this, we don't actually consider an explicit algorithm, but we just consider any algorithm that drives our system to somehow close to optimal states. And specifically, we consider the kind of states in our system that we are the most uncertain about in our dynamics. And this is sort of a theoretical foundation that I will not go into much detail to, but basically if we have an algorithm that drives us to this state, we can prove a theorem that says that we're guaranteed to converge to the maximum safe level set of our system up to a certain accuracy that we pick in advance after a finite number of data points. And we give a bound on how many data points you actually need in order to converge. And so as a last point, we do this without ever leaving the safe set. So with high probability, our system will remain stable. And the bound that we prove actually is very intuitive, namely it depends on how big is actually your safe set, how many assumptions do you encode in your prior model. Do I assume that it's very continuous or even linear? Or do I assume that it's very rough and nonlinear, and then I need more data points to explore? And lastly, it depends on the accuracy to which we want to learn this. So just to finish up, let's look at an example. So here we have an inverted pendulum where the maximum torque is limited, and we want to do safe exploration so that the pendulum doesn't fall down. We start with an initial AQR controller that's based on the mean model, that's our prior model, and we use the corresponding Lyapunov function. So here's the true safe set that we could certify if we actually knew the dynamics in advance. If we only used our prior model f of x, so the kind of not accounting model uncertainties, we would actually get an outer approximation of the true safe region in which our controller is safe to use. And this is clearly not feasible for safety critical systems. If instead you follow our approach, you start by a very small initial safe set in which you can guarantee stability, and starting from this, you slowly explore the system and get an inner approximation of the safe set. Importantly, see that all the data points that we've sampled here are actually within the true safe set. So our system never actually encountered stability during the entire learning process. With that, I want to conclude. Namely, we've shown that we can actually simultaneously learn about system dynamics and give stability guarantees. And specifically, we've shown Lyapunov stability for nonlinear uncertain systems using high probability guarantees and a discretization. And on the other hand, we've given convergence guarantees. And the upshot of all of this, that there's actually hope for doing safe reinforcement learning. So we're now actually working on a method which sort of gets rid of the assumption that, of knowing a Lyapunov function in advance. So we're optimizing over the Lyapunov function at the same time. And similarly, we optimize over the policy in a similar safe manner. So if you want to learn more of this, the code is actually open source. And if you want to see how we actually do the experiments, there are Jupyter notebooks online. And if you can, in general, care about safe learning, there's a lot more on my homepage. So thanks. Sure.
So, clarification. When you're trying to certify that this particular system is safe,
Yep.
you have to choose a particular Lyapunov candidate.
Yes.
And you're sampling that. But the system could be stable, but you're unfortunate at looking at the wrong candidate, right?
Yes, so this is a limitation of this method, but sort of as I was trying to point out in sort of the last point, there is actually a way to optimize over the Lyapunov function simultaneously using a large linear program, and this is sort of future work.
So you will use a template.
Yeah.
I just curious to know, how does the method compare with Gaussian process model that are different?
Sorry, can you speak up a bit?
How does your model compare with Gaussian process model that are different? They also have got theoretical guarantees in probability sense for that function. So
Sure, but I mean, here's what we're doing. So I guess the question is how this compares with adaptive control in general.
Gaussian process.
Gaussian process.
Yeah, sure. So I mean, so the main difference somehow is that we are sort of considering this entire pipeline and actually adapting sort of a specific policy online. So maybe we can chat about this online. So the differences are a bit subtle, and the theory behind it is actually quite different to give guarantees. So do I actually have time for more questions?
Maybe one last short question.
Sure.
In quantifying your uncertainty, you're sort of relying on the assumption that this G is in this conclusion connectivity
Yes.
space, and there are some, either you choose the kernel, or you estimate the kernel somehow,
So we
and
can't
therefore you have
estimate-
uncertainty. So the bounds, essentially, the confidence bounds that you come up with are strongly dependent on that.
Yes, so first of all, we can't actually estimate the kernel from data here because we're making the setup where we actually generate data online. So we can't estimate the kernel online. We rely on this in advance to give stability guarantees. So then it comes down to how much, so Gaussian processes in the end form a prior over functions. So in any safety critical system, if you want to give guarantees, you need prior assumptions. And it basically comes down to how much do you trust your prior, and if you don't trust your prior, then there's no hope of giving any guarantees at all.
Yeah, but the question is essentially how do you essentially tune or match your prior with your specific problem?
So we actually have a technical report on how to pick, so heuristically, the kernels for general nonlinear systems. I mean, maybe we can chat about this offline.